Crystalline water keeps coming and going in a stream of...
I grew up in Camden, New Jersey, which is an urban center, and I grew up in a family of 4 children. I am the eldest. My great uncle was a physician who was really the paterfamilias. He was my role model, and at an early age I knew that I wanted, if I were able, to become a physician. My interest in science and research really began once I got to university, and I went to the University of Pennsylvania as an undergraduate. I did a PhD in biochemistry there and my MD there as well. My first research experience actually was in a biochemical lab looking at the first paper I published was on the X-ray crystal structure of a small molecule that I synthesized. And in those days, now you could send off such a molecule and have the structure back in 2 days, but in those days I had to, write 2,000 lines of code and type them into punch cards and feed them into a computer after I synthesized the molecule, made the crystals, and diffracted X-rays from the crystals. So that got me interested in science in a deep way, and my PhD work was focused on really on what we call now structural biology, and it focused on conformational changes in the tertiary structure of actin in skeletal muscle, and used a variety of techniques from EPR to NMR to fluorescence resonance energy transfer. I synthesized most of these molecules myself because they weren't commercially available in those days to understand changes in the shape of actin during various phases of the contractile cycle. I came to Boston at Brigham and Women's Hospital, then Peter Ben Brigham Hospital, as an intern and resident in medicine, did a cardiology fellowship, was chief resident, and was uncertain what area of research to get involved in, but ultimately I focused on vascular biology and spent a lot of my career trying to understand various ways by which the endothelial cell, which lines the blood vessel wall, various ways by which the endothelial cell governs the normal homeostatic responses of the blood vessel and the blood that flows in it. And one of the molecules that I spent a lot of time thinking about is the small heterodiatomic nitric oxide molecule. And our contribution to that field was to appreciate that nitric oxide has effects not just on blood vessel tone, but also can impair blood clotting and protect the vessel from the adverse effects of thrombosis. Was to show that nitric oxide, can react with the functional groups of proteins, specifically sulfhydryl groups, not as nitric oxide alone, but as peroxynitrite or through thiol S-nitrosothiol transfer, to produce a form of post-translational modification, S-nitrisation, which comprises the bulk of available nitric oxide in tissues. And this was a rather exciting observation at the time. It was really the first post-translational modification that had been identified and characterized well following phosphorylation, which has been known for years. Now, of course, there are over 300 different forms of post-translational modification of the proteome that are known, but this was one of the early ones. And we were able to show that nitrisation could modulate protein function in a variety of ways. Exploring those mechanisms by which nitric oxide molecularly affected protein function and cell phenotype led me naturally to understand a bit more about the determinants of the redox state of a cell, since NO has a very complex chemistry. It's a deceptively simple molecule, but just understanding a little bit about the chemistry of nitrogen, you can realize how complicated it is. That took us off in a slightly different direction, and we explored and have been exploring several antioxidant proteins, 2 of which are kind of unique because they're selenoproteins. These are the glutathione peroxidases types 1 and 3. And these enzymes catalyze the reduction of hydrogen peroxide and lipid peroxides to their alcohols, the benefits of which are that they limit the derivatives from those peroxides which could inactivate nitric oxide chemically. And we had basic data, cellular data, animal data, and some patient data which supported these notions. What another interesting feature of these selenoproteins is that, of course, selenium is the 21st amino acid. When it's organified in proteins, it exists as selenocysteine, in which selenium is substituted for sulfur. As my colleague Vadim Gladyshev has pointed out, evolutionarily speaking, selenocysteine is primordial to cysteine, because the more reducing environment in which early life formed required a different redox potential for that functionality, and only with progressive oxidation or increase in the reduction in the reducing potential of the ambient environment did selenocysteine evolve to cysteine. The codon for selenocysteine happens to be UGA, which is a stop codon. So a question that was addressed by people like Tressa Statman and Peter Neuberger was how does the ribosome recognize UGA as coding for selenocysteine rather than terminate translation? And it turns out that the mechanism for that has to do with an element of tertiary structure, of secondary structure in the 3' UTR, and 3 or 4 cofactors, translational cofactors that stabilize the message on the ribosome. And what we, among the contributions we made in that area, include identifying novel ways by which certain drugs affect selenocysteine incorporation. There's a class of antibiotics called aminoglycosides, which were designed to read through stop codons in bacteria. As it turns out, their toxicities in the host include ototoxicity and renal toxicity. And we showed that a mechanism by which to explain that toxicity is that the aminoglycoside causes a read-through of the stop codon in these selenoproteins to misincorporate arginine in the case of glutathione peroxidase type 1 instead of selenocysteine, which makes it inactive. That causes oxidant stress in these organs and the damage that has been observed. So I give you these examples because it shows this transition and translation between clinical observations and interests and pretty basic observations and interest. And I've always had a foot in both camps. Physician scientists like myself, and there are unfortunately fewer of these now than there were in the past, people with my phenotype, I think provide a unique insight. The pure PhD understands the trees, but maybe not the forest. The pure MD understands the forest, but not the trees. And a person who can straddle those two worlds, I think, adds value to our understanding of the biological enterprise. That's what I've tried to do for most of my career. The stimulus for that in the basic lab was my effort to understand the metabolism of nitric oxide and how it's synthesized, how it's oxidized, the reactions in which it's involved as a means of modifying proteins post-translationally, and the biological effects of all of these different species. And the reason I became interested in that was that there was a growing interest in simple treatments that could promote or reduce nitric oxide bioavailability in humans. If you go in a health food store, you could buy arginine as a way to stimulate nitric oxide synthesis, so they claim. Of course, arginine has a host of other potential actions, so that it drove me to consider in its totality everything I knew or could learn about the action of nitric oxide in biological systems. And as I began to build these networks, I realized that I couldn't address the questions I wanted to address, namely, how can you change the concentration of one species in this network without affecting all of the other species? I couldn't address those kinds of questions without gaining more of an understanding of nonlinear dynamics and network structures and their determinants.
So then you went from, from crystals in the beginning, then to nitric oxide, which is a very, very simple, it's NO, yeah?
Yep.
Exactly. And then from there, you started exploring the world in which NO lived, and from there you moved into actually the network that we are. And now you're moving even out, and we talked about, the network that we are, but the network that we're part of also as humans, and how that does affect us for health.
Yes.
Yeah. Well, Joseph, it has been a pleasure having you on Cambridge Nights. It has been wonderful, and we hope to have you here also again in the future.
Thank you very much, Cesar.
Thank you.
It's my pleasure. Thank you.
Crystalline water keeps coming and going in a stream of wonders. It follows meanders, falls and it splashes into millions of bubbles. Play hide and seek in the castles of sand. How's that for?